Hi, folks. So I guess this is I'm just gonna pre-record this and you'll have a look through at your own leisure. As you can tell, I'm in a hotel in Paris. Say hi, Paris. And I don't have a whiteboard. So we're gonna try and do this a little differently than we normally do. And in particular, one of the things that we're gonna focus on is we're going back to this idea of the black body temperature, how we get this as a concept, and what the ultraviolet catastrophe was. So this will be a little bit of a history lesson. So for folks who maybe haven't thought long and hard about how we got to where we're going, I do think this is important because it's always helpful to kind of see what the state of physics was and how they made these advances. To do this, I'm actually not going to use slides for the first part. So we're going to use, I found this really cool set of lecture notes, and I'm going to attempt to walk you through them. And where I can, I'm going to be adding like notations in to the text if that works. And if it doesn't work, I'll try and throw up a whiteboard. Um, it's the start here, so I think this will take maybe 45 minutes. But go ahead and work through that process on your own. If we don't get that far, that's perfectly okay. And then for Thursday's lecture, I'll record some of the slides instead. Okay, so I'm going to stop the video here and try to share this. The first thing to keep in mind is we need to go back a little bit. And we really need to think about the state of physics in the late 1800s and the early 1900s. So this is before quantum mechanics has been discovered, or I should say formalized. And in particular, some of the things that we want to remember is things like Stefan Boltzmann and Kelvin, Lord Kelvin of the unit Kelvin. They were doing statistical mechanics, and what they were doing was they were discovering the energy of systems by looking at aggregates of individual particles. And so, for example, this shape here, this is the spectrum of black body, which you know and love. But for example, this dimensionless quantity, which is h nu, nu being the frequency divided by kT for a given object, they tended to measure out here. What that means is these would be the higher frequency observations. Or sorry, I should say this differently. So this would be the ones that we're going to be looking at will be in the higher wavelength, lower frequency. Um, and in particular, I want to show you what happens when you have some approximations, in particular for something like here's the Rayleigh-Jeans law. So this is an empirical law. And what this essentially says is that the energy for a given frequency is proportional to the square of the frequency. Okay. All that means is as you get higher and higher energies, as you get higher and higher frequencies, you get more and more energy. And we'll talk about how this leads to the ultraviolet catastrophe, which is alluded to here. But essentially, you can see that this approximation, this nu squared approximation, is the very first part of, sorry, let me go back here. Here we have some quantity x squared. And if you don't have this thing, this e to the x minus 1, this thing doesn't flip over, right? And so the energy just keeps going up and up and up as the frequencies go up. And of course, that's not physical. So one thing that I want to take us back to is this idea of how do you get black bodies in the first place? So by definition, a black body is something which is in thermal equilibrium with its surroundings, and it has the properties that it is not going to retain any heat. What I mean by that is if there's light that's incident on it, it's fully absorbed. And then because it's staying in thermal equilibrium, it gets rid of that heat in some way or another, right? So it's not becoming hotter. And similarly, you can imagine that if there is an internal source of heat in this black body, then it's radiating at exactly what the temperature of that internal source would be. Okay. So eventually we're going to get to here and we'll talk about Planck's constant and whatnot. But first, I want to start by thinking about what we're going to do. So we need to understand some of the properties of waves. And so if you're doing ENM2, hopefully you've seen a little bit of this wave work. And if you haven't seen it, um, just go ahead and think back to, say, the 2500, 2510, when we're thinking about waves on a string. And a lot of the physics is going to be the same here. And the only thing that we're going to introduce that'll be a little unusual will, of course, be the statistical mechanics part, which is where you're summing over the states. And then we'll need to talk about Einstein's photoelectric effect. And you may or may not know, for example, that Einstein has only one Nobel Prize. You're thinking to yourself, well, that must be for special relativity, or that must be for E equals mc squared. And in fact, it's for neither of them. It's for this thing called the photoelectric effect. So if you're not familiar with what that is, we need to understand why this was such an important piece of physics in the first place. Okay, so let's first think about waves in a box. And of course, here's your properties of a wave. There's your wavelength from peak to peak or from trough to trough, however you want to describe it. The amplitude is here. And we can define this in any number of ways, but essentially we're going to use something like the sine and something like the distance. Okay, and that's if this is r, then this is giving you a as a function of r. We can usually write this in terms of a wave vector. So this has a direction that you take the dot product with. We notice that these are both bold. And of course, the magnitude, of course, is just them dotted into one another. Okay. If the wave is moving, then not only do we have the positional piece, but we also have a piece that is dependent on k. Oh, sorry, on t. So as time progresses, you can imagine that the wave is moving left or right, depending on what the value of kc is here. And so there's some nice relations, and I encourage you to go and look at the wave equation that you may have seen in the 2500 textbook. But essentially, this is the easiest way to write any sort of sinusoidal wave, and that is simply the amplitude times a sine or a cosine, depending on whether or not you want the amplitude to start at 0. Kr, this is the spatial component where you are along the wave, minus omega t, which is how the wave is progressing. Okay, so we're going to use this formalism here because we want to think about electromagnetic waves in a box. Okay, so the first thing that I want you to consider is a cubical box of length L, and that there are waves bouncing back and forth. So if that's the case, then the box has, let's say, fixed walls, they're perfectly conducting, and the electronic field at the boundary goes to 0. So that means that we're not going to have any cosine solutions here. We're only going to look at the sine solutions. So this would be an example of one that works. So here is a box of length L, and here is a sine wave whose wavelength is 2L, right? And you can see that here, the L, there's the wavelength, and one of them fits perfectly in here. This would be an example of one whose wavelength is L, right? And then this one, of course, is L over, or L times 2/3. And what you can see is all of these versions, they fit inside of that box, and they don't overextend on either side here. And because of this, these would all be solutions to the wave equation inside that box. And generally speaking, you can see a little bit of a pattern in the wavelengths, right? So for example, this one here was 2L, this one here was L, and so on and so forth. And what you can imagine is you can create a little integer math here just to describe how the different wavelengths. So this is your box length, and this is some integer L. And here's the wavelength that you have available and how many of these you can get in, right? So as you double or triple it, you're going to make, say, the wave go from a bigger wavelength to a smaller wavelength, but this is happening in integers, right? Okay, so then we can say something along the lines that kx, well, kx is the inverted part of the wavelength. So it's just 2 pi divided by the wavelength. And this would be the component of that wave vector k that we saw before. That's going to be in the x direction. So assume that this is a 3-dimensional box, but I'm only going to look at each dimension individually. right? And so essentially, you can repeat this. You can say, well, there's no specific reason why X should be different than Y or Z. This is a square box. And so you get the same formalism for all of them. Hey, here's pi L over big L, and L is the length, and little l is the integer of whatever wave number you're talking about. So for example, you can't use 2.3 here because the wavelengths won't work out and the sign won't go to zero at the edge. They need to be integer multiples, right? Okay. So now let's imagine you have a three-dimensional diagram, right? And this shows all of the allowed values. That's what this thing is here. And this essentially says, okay, so for a given value of L, here's all the M's that are available. And you can only use the dots, right? So you can use 9 and 1 or 9 and 2 and so on and so forth, but you can't go all the way up to here to 9 and 8 for a given width in this uh, um, K vector space. So the reason that I say this is because we can think about the different modes of oscillation in X, Y, and Z as being the product of these various components. So what I mean by that is the wave in X does not affect the wave in Y, and so on and so forth. And so here we have the product of the three, right? You may or may not be familiar with the wave equation. So the wave equation, let's see if I can annotate here. Generally speaking, oh yeah, this works. Let's go, baby. Okay. Oh, undo that one. Sorry about that. We're going to try our best here. So this is the wave equation in two dimensions. And generally speaking, we can use something like phi, and we're going to say it's equal to 1 over the velocity squared, d squared d, oops, t squared of phi. Okay, so let's just understand that for a couple seconds. So on the left-hand side, we have a double derivative with respect to space, and on the right-hand side, we have a double derivative with respect to time. And when we think about these two things, we understand that there is an English, a non-mathematical way of interpreting this. So what is the double derivative of an object? Well, the first derivative is the slope, and the second derivative with respect to space is the curvature. So on the left-hand side, this is saying that the curvature of phi, some function phi, is going to be equal to something else. So let's look at how the curvature is related to this other thing. And on the other side, you have 1 over v squared. That's a constant. We're going to worry about that later. And then you have a double t derivative here. So we know, for example, that if this were talking about something like x, then this would be like the rate of change. You know, dx dt would be the velocity, and then dv dt would, of course, be the acceleration. So if this was talking about a position, then this would say that the acceleration was on the right-hand side. And this is kind of how we can interpret both of these. So for example, on the left-hand side, we're talking about curvature. On the right-hand side, we're talking about acceleration. Okay, so what does this mean? This is how you get a wave. If you imagine, here you go. Here's a really perfect wave. Wow, good job, Krismani. You're so good at drawing. So let's think about any single part of this wave. And you can imagine this as like a string, and you've plucked the string on a guitar and it's making this cool little wave. Where does it want to be? Well, it wants to be, I'm going to attempt to do a dotted line here. Hopefully this is showing up for you as well as it's showing up for me. This is maybe the rest position, right? So this is like the zero motion away from this. And let's say that this here, that's the amplitude of the wave. I'm going to call that phi just for a second. Oops, fuck. Let's call that phi. There we go. Okay. So if, for example, I have this string and I haven't plucked it yet, it'll just sit there. And in that particular circumstance, the curvature is zero. And so therefore the string won't move. Okay, perfect. That makes a lot of sense. Whereas once I pluck the string, all of a sudden there's curvature. And depending on where this curvature is, it's going to say what the acceleration is. Okay, so let's have a look at the curvature. This is concave down, right? Negative. So the acceleration is going to be downwards. This is concave up. The acceleration is upwards. Oh, okay. So this is the direct relationship between the idea of curvature and waves, right? And that's just even before we start to think about how do we solve these types of problems. Now, of course, you're familiar with that shape. You're like, okay, that's a wave. But one other thing that's very cool about these double derivatives, of course, is that we have special functions that when you take two derivatives of them, you get the function back, right? And so the cool thing here is that I'm gonna choose something where I take two derivatives of space and two derivatives of time, and they're going to be the same function, just off by a 1 over v squared, right? And that is by definition the wave equation. Does that make sense? I mean, I don't know why I'm saying that because I can't hear you. So hopefully it makes sense. Okay, hold on. Let me clear. How do I do that? Okay, here are the drawings. Okay. All right. So this is how you make waves. Okay. Oops. And you can create a wave dimension vector. That's not something that we particularly care about, but here is what we do care about. We want to count the modes. And the reason that we want to do this is that if you want to think, in the 17, 1800s, they were moving away from the ideas of like heat was a fluid. So, for example, there used to be thought that heat was a caloric quantity, like something that was like a liquid that moved from object to object. And of course, this is before we really understood the statistical nature of heat. Um, when you begin to understand the statistical nature of heat, you understand that the reason, for example, you have an ideal gas and it has a temperature that is proportional to other quantities. And yet, for example, O2, say oxygen, two oxygens who are a gas, have a different ability to carry heat than, say, hydrogen. And of course, you can correct for the mass and everything else. But you find out that there are degrees of freedom. That means ways in which the atom or molecule can store energy, right? So, for example, if you have something like um, diatomic molecule, it can rotate and it can act like an accordion where it's moving in and out. And that allows additional modes of freedom to store energy, right? As opposed to hydrogen, which doesn't have that ability. There is no rotating hydrogen, for example. Okay. So in general, we want to think about how we add up the modes of oscillation. For example, in this case, we're talking about the oscillation of a wave. We're not talking about the internal degrees of freedom of a gas, but you'll see how they're very similar. And all you're going to do here is think about in some frequency range between nu and nu plus d nu, I can convert that very easily to k-space. And I have these beautiful equations here for the wave. And so I'm just going to think about how I can convert this into the number of states within some radius r. Now you need to be a little careful here because typically we use p for something like momentum, but I didn't write this, so this is something that I found off of the good old handy dandy internet. And just think r here. So I'll try and say that, but if I make a mistake, go ahead and correct that in your mind. And the thing I want to talk about here is the number of states of a given r. Okay. So let's imagine a sphere. Okay. So the volume of a spherical shell of radius r and thickness dr, of course, is that You have some sphere. This is going to be your 4 pi r squared dr. So that's in the direction of the radial direction, right? And so number of modes possible here is your spherical component, the thickness, and 1/8 of them. So you only have to consider an eighth of the sphere. Okay. All right. So if we go through and we think, okay, so this is how I write K in terms of these quantities. Instead of X, we're now using P. And similarly, instead of dk, we're now using dp. Then I can write the same thing that I wrote up here, but I'm going to write in terms of k. So this is the same thing as this, just in terms of k. And of course, L cubed is v. So you can write that as the volume of the box, right? And this is nice because if we have anything that has a volume and then later on we divide by the volume, then it'll just get rid of this v. So we're going to hold it like that. And we're going to rewrite this equation in terms of here's your Ks and here's in terms of your frequencies. Okay. And then they just clean this up a little bit. So it has all these pieces. Okay. For electromagnetic waves, there's always two independent modes or polarizations per state. So you get to double the number that you're counting. And the bottom line is essentially that you have something that looks like this, which is the number of states is 8 pi frequency squared over the speed of light cubed times the volume dV, or sorry, d frequency. And of course, I told you that let's do this per unit volume. So let's get rid of this V so that this is the equation that we're considering. So what am I saying? I'm saying that this is the number of states that exist for any wave that you might find, right? In 3 dimensions. Okay. All right. So now let's find how we're heading towards an ultraviolet catastrophe. And you can kind of already see the problem, right? Because as the frequencies go up, okay, number of states are going to go up. And I think if you're remembering from your stat mech, the number of states going to infinity and them all being populated is not going to be good for energy, right? So let's go back to this idea of thermal equilibrium, okay? In the case of the I don't know how to say this properly for folks who maybe haven't taken stat mech. So if this is over your head, go ahead and write this down and we can discuss this more, some of the background. But essentially, we get to award 1/2 kT to each degree of freedom. Okay, what does that mean? It means if you're in thermal equilibrium, you have enough ability to exchange energy between the modes of oscillation. So, for example, let's go back to our diatomic molecule, and you have one mode which is, say, rotating, spinning around an axis, versus oscillating, say, back and forth along that same axis, but like an accordion. And so, if you have a big gas, and you just let it sit there. Remember that thermal equilibrium means that you've waited long enough for the system's temperature not to be fluctuating and that the gas is in equilibrium with the container. So if that's the case, then it would be very unusual to find some portion of the gas in which it was only rotating or only moving like an accordion. So generally speaking, when you think about the statistics, right, we talk about entropy being maximized and the gas wanting to take up all of the possible forms of entropy. So we would be very surprised to find that the gas would be in this unusual state, right? Where like a small fraction of it is not using some of the modes of oscillation that are available to it. And in fact, we don't, right? When we look at gases as a whole, this is what we find. We find that they are going to put 1/2 kT into each degree of freedom that they are afforded, right? Okay. And if you wait long enough, they have the same average energy when the system is in thermodynamic equilibrium, right? So what that means is that I can make a statement here about the total energy density. Because all I have to do is I have to take the energy density, which is du, and really what this means is that if I have the average energy and I multiply it by the average number of states, oh, sorry, if I have the average energy and I multiply it by the number of states, not the average number of states, then I'll get the total energy because I can just integrate that, right? And similarly here, I can just have a look. Here is the energy per unit frequency, right? And if the energy per unit frequency is simply the number of states, which is this part here, times dV, times this average energy, then this differential, is perfectly fine. I can just write U and I can just have it like this, right? Okay. So let's look at a harmonic oscillator in thermal equilibrium. Okay, so we found, not us, but you've found perhaps in another part of either thermal or in 2500 that the average energy for your harmonic oscillator by definition is kT. Okay, this is like the way that we think about a harmonic oscillator. And if I do that, if I put this definition in here, this is saying this is the thermal equilibrium, right? Energy is kT. This is a representation of temperature as energy, right? And here again is where you begin to have the problem. Okay. The energy density, the energy as a function of frequency, okay, at zero, no big deal, right? This is well behaved at small nu. What happens at large nu? Goes to infinity, right? This is the ultraviolet catastrophe. This is saying, okay, while this definition works really well for things like radio waves, for things like microwaves, even in some ways for things like the infrared and perhaps the visible, it gets bad quick as you go towards the ultraviolet, right? And what this is essentially saying is if you integrate from zero, and I know zero frequency is something that perhaps we don't think about very often, but that would be the natural bounds here, right? From zero to infinite frequency. And both of these are non-physical bounds, but in the context of what we're thinking about here, you can't have infinite energy. So you have a problem on both sides, right? This is the ultraviolet catastrophe, and this empirical law, this Rayleigh-Jeans law, this was known. Um, and as they were going through trying to explain how classical physics could talk about light, this is at a point in time in history where we weren't sure whether or not you could use electromagnetic waves in the same way to describe them with this statistical physics, etc., right? And this seemed like a problem. This is telling folks, hey, we don't quite understand how light works because our expectation should be that for any box with high enough frequency, you can get infinite energy out of it. And of course, you don't see that, right? So, whether that is um, some forge, for example, where you're melting iron. That's a very finite temperature, and that's the temperature necessary to, say, melt steel. But it doesn't cause the entire world to explode due to infinite energy, right? Okay. So this was derived in the 1900s, and uh, Lord Kelvin, of course, I don't know if you know this, he had a famous quote. And he said, I think we figured out almost all of physics. There's just two dark clouds looming on the horizon. What he didn't know at the time is those two dark clouds would end up being special relativity and quantum mechanics. And that would fundamentally change all of modern physics, and be responsible for all of the technology that you have in the modern era, right? You don't get any semiconductor, you don't get like telephones. I'm not recording this for you without quantum mechanics. Quantum mechanics is the most tested scientific formalism in history, right? Okay. So let's go back to this other idea. So why does Einstein then get a Nobel Prize? He didn't work in quantum mechanics, right? Well, not exactly. So let me take you back a little bit farther. So in 1905, there was a revolutionary paper, okay? And Einstein basically said light should be considered as a particle, okay? That's weird. In 1905. Lights are waves. But there is enough laboratory evidence to suggest that perhaps maybe this is a weird way of thinking about them. So he is looking at a body of empirical evidence and trying to understand how, what are the properties of light. He's not just sitting there by himself thinking about nothing. In particular, he's thinking about some experiments, such as the one that's shown here on the right, where you may have, say, a quartz window in a vacuum. You shine incident light, and it turns into electrons. And in particular, this is a demonstration of the photoelectric effect where you can turn light into electrons, noticing that they have the same forces associated with them. And um, some of the work that he was doing was to say if you make these things photons, you have to give each one of them a specific energy. Okay. So not only is light a wave, like this. It has wave properties, but it's actually just like a piece. And then it like hits, okay? And that has a specific energy. As opposed to a wave, right? And this is where the idea of our analogies tends to go awry. Because if I sit at the beach, you can't ever just think of one crest of a wave, right? Um, the analogy of a wave like this is the wavelength. So if I cut it here and here, that's different than any of these other pieces. The wave is not described in that way, right? And yet you can have a pulse that delivers energy of this characteristic frequency, nu, and this h, which is Planck's constant, which turns out will be very important. Okay. Okay, so one of the things is that the puzzling aspects of the photoelectric effect was that this voltage that you got was always the same. And what I mean by that is that the kinetic energy that the electrons acquired had a maximum value, independent of how intense the radiation was. So what I mean by that is you say, um, let's say you change, let's see how to say this properly. Okay. Um, Here's your potential difference, and I guess it's just easier to show you these ones. Here's your potential difference from the anode and the cathode from this object above. Here's this sliding contact, right? Here's your voltmeter. This is the current going through the system. Okay, and what you can do here is you can say, okay, um, let's think about the work. Let's think about the energy required to remove an electron from the surface of a material, right? In order to create the charge that you're measuring. Okay. So let's imagine that you have some amount of work necessary to remove the electron, and then the electron has some speed. Okay. That's sort of a natural thing. Okay. And that'll be equal to the thing that we use to liberate the electron, which is just the light. Okay. So the maximum kinetic energy of the ejected electrons is found from something called the stopping voltage. Okay, this is some V naught. Okay, and the current ceases to flow when this is true. So all we're doing here is we're taking this idea of the kinetic energy of an electron and we're turning it into the electron charge times a voltage. Okay. So what this means is that you can think about the light in this experiment as doing the work necessary to um, remove the electron, and then as soon as it's liberated, it has some internal energy. Okay. Okay. So this is really interesting because this suddenly allows us to write new in terms of these other objects. Okay. What I mean by that is go ahead and see what happens here when you divide by h. So now you have your work function. This is the amount of energy necessary to liberate them, divided by h, and EV naught, also divided by h. Okay? But look what's missing here. Okay? Increasing the intensity of the light. increases the number of electrons of energy, this amount, but does not change their individual energies. So let me say this slightly differently. Okay. So I'm gonna try not to use an analogy here because I think you really can just think about this and see how strange this is. I'm shining, let's say something, I don't know, I don't have this built at home, but let's say I have some lamp that I can go through all of the colors of the light and I can get it up to ultraviolet or whatever, right? And I change the intensity of the light, and what I produce is more electrons, but not faster electrons. Does that make sense? Okay. Okay, so this was the idea. So this is the photoelectric effect, and this showed that the dependence of well, sorry. When this was derived, the dependence of um, what do they call this? The stopping, the work. Oh goodness, the work function, and this inherent potential difference. We didn't know how it depended on the frequency of the light. Okay, but you can go and you can find these all out in laboratory settings. This is all done in the lab. This is all done before the theory necessary to understand it, right? Um, and even though Einstein comes along and makes this prediction, this is all done in the lab afterwards. And they measure these all, and they say, this is, I think, I forget when he did this in 1905 or something. And 11 years later, Millikan proves the photoelectric effect, right? And this is what Einstein wins the Nobel Prize for. Okay. So this is the first example of the wave particle duality, right? Particles having wave-like properties. And we'll get into why that's so fucking weird for matter, if you want to. Um, but in particular, this is sort of strange for 1916, right? Because he says, this is from Millikan. This is the one who did um, he also did the oil pitch experiment and the whether or not we're flying through an ether. So really great work that him and his group did. But he said, we are confronted, however, by the astonishing situation that these facts were correctly and exactly predicted 11 years ago by a form of quantum theory which has now generally been abandoned. So what was he referring to? He was talking about Einstein's view of quantum mechanics, which said, I think that the energy inside light is quantized, and that E is equal to the product of the Planck constant times the frequency. Okay? And that it comes in little itty bitty things called quanta of light or photons, right? He talks about Einstein. He says, he's bold, not to say reckless hypothesis of an electromagnetic light corpuscle. This is just like a little piece of energy h nu, which flies in the face of the thoroughly established facts of interference. Now, what do we mean by that? Well, of course, you have these experiments, such as the double slit experiment for light. Sorry, let's just be clear about this, where you have interference of waves, right? So light is a wave. That's been shown, certainly, many, many times. This is in contrast to the optics of Newton. And what Newton found was that if you treat light as though it's a particle that's bent through a prism, or through a lens, then you can very accurately describe the actions of light and how light bends. Now, that's not perfect, of course, because you know, they were also finding out that light had wave-like properties. But the idea that light was a particle, a single corpuscle of energy, they were like, that's fucking crazy. You're nuts so but so, right? And yet here's it working like that, right? Okay. So that's all the historical parts here that I want to talk to you about. So you have to move from this idea of waves and waves inside of a cavity and how that leads to these energy states just going crazy at high frequency. And then we can resolve this by remembering that every single wave, right, is really a particle and it's called a photon and it has a specific energy, right? Now, the cool thing is that, of course, we can change those frequencies. There's an infinite number of frequencies that we can go between zero and infinity, right? That's by definition of infinity. But the sheer number of particles, the number of photons is particularly important. And I'm going to show you how just slight adjustment is going to save the ultraviolet catastrophe, right? So now if I have an energy, right? So let's say E is equal to N times H nu, okay? So N would be the number of photons in this mode for whatever this for whatever this energetic state is, right? And what we're going to do here is we're going to say, let's keep them in thermal equilibrium at temperature T, okay? There's got to be some ways between exchanging energy in the modes and between the photons, but we don't really care about the details of that, right? And instead, we're going to use the Boltzmann distribution to see how occupied the modes are. Now, if you're not familiar with the Boltzmann distribution, this is certainly something that you'll see in your statistical mechanics. And this essentially just has, it's a probability. And so, for example, if you want to do probabilities, let's say we want to talk about what's the probability of, here, let me annotate again. What's the probability of two heads if I flip two coins? Okay, so here's a coin and here's another coin. Okay, so in order to find the probability of getting two heads, that would be H, right? That's the probability, or that's the state that I want to understand. I need to enumerate the other states. Okay, so that would be tails, heads, right? Oops, fuck. Anyway, you get the idea. Heads, tails, and of course, tails, tails, right? And so the probability is 1/4. And all I've done is on the bottom, I've enumerated all the states. So this is all of the states. And on the top is the one I want, right? Okay, let's pretend like I'm really good at this type of annotation. Okay. Oops, whatever. Fuck it. Okay, so this is the idea of a Boltzmann distribution. This is the probability of a single mode having that energy, and Boltzmann's contribution is here in the exponential. That was in noting that the exponential states are like this. Um, Most of them, if the energy is zero, then you have them all in the ground state, for example, as opposed to higher up, right? Okay, let's clear this all out. Okay. So if we do this, this tells us the probability, okay, of particles being in a given state. Oops, fuck. Sorry, let me stop this annotation. There we go. Okay. So this means that the mean energy of the mode of some light of a frequency nu is going to look like this. Okay. And this is going to be a little confusing, but let me just walk you through it really quickly. Here's the energy per unit nu. This is the average. So to find the average, you really have to take an expectation value. For folks in statistical mechanics, you'll understand what that means. And that is the energy per state multiplied by the probability that you're in that state. And then you add them all up. You add up all the states. So if 80% of the states are in the 0th energy level, you multiply 80% by whatever the energy of that state is, right? Plus, let's go to the next one. Let's say there's 13 in that next one, plus the energy in the first state, so on and so forth. And so this is essentially giving you a weighted average. So instead of looking at all of the states and dividing by the number of states there are, you take the probability that you're in that state and then you add them all up. And this probability is already giving you the weighting. And you'll notice that that weighted average, of course, if all states are equally likely, let's say you have 10 states, Well, then by definition, that's 1 over 10, and you return the definition of an average, right? Okay. Hope folks are seeing that. Okay. And that just leads you here on the top to take the ratio between the energy per unit state divided by the total number of states. This is the total number of states, right? And then you just multiply them up here. So this is the probability. Okay. You can turn the energies back into these NH news. Okay. So this is the number of the state number that you're in, and this is the frequency. Okay. So we can simplify this a little bit. Um, and you can take the word X or the letter X to be this mess here, not the N, but this mess. So you have N X to the N. And if you write that out, you'll see that you get a series expansion here. And this series expansion looks like this. Okay. So the mean energy of a single frequency is E bar H nu X. Remember, X is that thing from before, 1 minus X. And the best way to rewrite that is like this, X to the minus 1, minus 1. Okay, and then we put X back in, we put the minus 1, we're going to flip that around, and that's like this. Okay? Okay. So what does this say? This says this is the average energy of the mode nu, according to the theory in which light is quantized. Okay? So this is really, really helpful because let's think about how the frequency changes. Frequencies go off to infinity. Okay. E to the infinity is correct. Infinite. Infinite over infinite, finite. Right? Okay. What about this one here? To find the classical limit, let's have it head towards 0. Okay. As this head towards 0, this whole bottom part acts like 1 plus h nu over kt, right? So, because the ones are going to cancel here. So you end up with something that looks like h nu over kt. And at small values of h nu, there's h nu on the bottom, h nu on the top. It looks like kt, right? Okay, so here's what you're getting. You're getting that the average energy at low frequencies behaves like it did in classical. But now we don't have the problem of nu as it goes to infinity of having infinite energy, right? Okay, and that's the idea of the expression for the average value of an oscillator in thermal equilibrium. Excuse me, thermal equilibrium. Okay, so now we're almost there. So now we have this definition of E nu, as a function of nu here, and we're going to use this definition in this differential. Okay, so here's your nu squared. This h nu on the top is going to become h nu cubed. And on the bottom, this is the piece that you're going to do the integration with. Okay, so here is your Planck distribution function, right? You wonder where this thing comes from? This is it, right? And so when you make that shape that we see over and over in class of the blackbody function, it's this. Okay, it's the h nu squared is up here. Sorry, the nu squared is up here, and then this piece with h nu e to the h nu over kt minus 1, that is the energy per unit density, and this, of course, is the number of states. Okay. Okay, I realized that was a really long way to go. I hope that some of that was helpful, if not just for historical reference, but for also seeing sort of like how we go about this process of using the Planck function. I'm going to stop the recording here. I know maybe we didn't get quite as far as we would normally would in class, but there wasn't really a lot of like back and forth. So I strongly encourage you to rewatch and to pause, see if you can go back and understand some of the things here. If you want to send me messages on Slack or by email, feel free to do that. We can talk about them more in office hours as well. And yeah, if this format works, we can do it again for Thursday's class, and then I'll go through those slides a little better. Um, but if it doesn't work, if everyone's really upset about this, let me know right away. And I will also just put that PDF that I found. I'm going to put that on Canvas as well, so you can go through it at your own speed and try to understand it a little better. Okay, folks, sorry that I'm not there with you this week, but hope everyone's having a great week. Bye now.